All right, let's take a look at multiplicity of polynomials along with end behavior and all kinds of good stuff like that. It'll be great times, just like always. So let's jump right into these notes here. So we're going to be looking at polynomial functions. Those are those functions that have nice round exponent numbers, whole numbers, positives. As you can see here in this gigantic mess, right, we have these numbers here and they go down by 1 possibly. They might skip numbers, as we'll see here in a second. It's possible to skip. But today we're going to look at what the general shape of these things are, as well as what the end behavior is. And we'll talk briefly about what multiplicity is. That's kind of a crazy word, what it tells us about the graph. All right, so jumping in here. So a cubic, we've already looked at linear functions and quadratics, so we're graduating up to higher degree polynomials. So an x to the third function would be a cubic, and this is degree 3, of course, not 3x squared, but just 3. So what are the shapes of these cubics? So they do this on the ends, that's called end behavior. And we'll talk about that here in a second. And they might have a little dip in the middle. They might have a dip. Now, over on the right side, I see a vocabulary word that we've talked about before, zeros. What are zeros? They are x-intercepts of the graph. They're where the function spits out 0. That's why it's called a 0. How many times could this graph, at a maximum, hit the x-axis? How many times could it hit? Well, if you imagine me drawing an x-axis here, you see that it could potentially hit 3 times. It could potentially hit 3 times. You see that there? Let me zoom in a bit. It could potentially hit 3 times, so 3 zeros. Notice that's the same as the degree. Hint, 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 same as the degree. All right, quartic. What a fun word, quartic. Quartic, like a quarter, it has implies the number 4, doesn't it? So a quartic is an x to the 4th, which is degree 4. It could possibly have 4 zeros. You see all that? Now, what on earth do these have? Now, that's an even exponent. Even exponents, like an x squared, do this on the ends. That's called end behavior, which we'll get to in a second. So these graphs look like this in the ends. And then they might have one little hill in the middle. One little hill. So you can imagine, again, if I were to draw an x-axis in here, it could potentially hit 4 times. Now, could it hit 3 times? Could it hit 2 times? Yes. If I drew the x-axis up here because maybe it had been shifted down, now it only hits twice. Could I make it hit 3 times? Yes. If it just hits here, here, and here, that's 3 times. So at a maximum, it could hit 4 times. At a very maximum, 4 times. All right, some sort of polynomial, any sort of polynomial. Here we'll do a 5th degree polynomial, would be x to the, let's say, let's go ahead and let's do 5 here. I forget exactly what I was meaning to do in these notes. If I was supposed to put an n there, I just wanted to do this. All right, so 5th degree here, or x to the n. Let's just add it in. We'll do both. There it is. So x to the 5th, this is degree 5. This could have 5 zeros. It's called a quintic, but we don't call it a quintic, frankly. We just call it a 5th degree polynomial, 5th degree polynomial. All right, so that's an odd degree. Odd degree means it's going to be doing the whole, I got to do it right here in the camera, this way and this way, but then over here on the left. So it's going to look like this. It's going to look like that, just like an x to the 3rd. But unlike an x to the 3rd, it might have an extra hill in it. It might have an extra hill in it. So let me draw an imaginary x-axis. You see how it could hit 5 times? That's an x to the 5th. An x to the 5th could hit 5 times. All right. And then a degree n polynomial could have possible zeros, n. Now, these could look like this in the end behavior with some extra stuff in the middle, right? Or they could look like this on the ends with some extra stuff in the middle, just depending on what the exponent is. So if it's an odd degree, so this would be x to the n, where n is odd, the degree is n, possible zeros is n, and the shape will be like this, folks. All right, and it will have something going on in the middle, possibly, and it will have n zeros. That's an odd degree. Now, what about an even degree? X to the n, where n is even. Just think about a parabola, x squared, ends like, goes like that on the ends. So in the middle, it might have some extra lumps and things, hills and valleys, just depending on what that degree is. All right, so these are polynomial functions. So I mentioned at the beginning of this video that we've got this concept of multiplicity. What on earth does that mean? In factored form, so let me highlight that to really make it stand out. In factored form, the exponent on individual factors is the multiplicity. So you can see an example down here at the bottom. You see how these are called factors. We have a factor of x minus 2, a factor of x plus 1, and a factor of x minus 1. So what we would say is that let's write this down. X minus 2 has multiplicity of 3 right here. It's there 3 times, right? Like x to the third is x times x times x, 3 of them. So that x minus 2 factor is there 3 times. Easy enough. All right. What about x plus 1? X plus 1 has multiplicity of 2 because it's there twice. And then finally this last one, x minus 1 has multiplicity. What's the invisible exponent on that? There's 1 factor sitting there, so we say the multiplicity is 1. Now, the number 1 is an odd number, right? The number 3 was an odd number. And then this is an even exponent. Now, I haven't told you what that tells us yet. Ready? This is really cool. I think this is so cool. Odd multiplicities means the graph cuts through the x-axis right there. Like goes right through the x-axis. Cuts through the x-axis. I'll show you here in a second. And then even multiplicities simply what? What is sort of the opposite of cutting through? It's got to touch it because it's a 0. Remember I said it was a 0 there. So it's got to touch it. It simply touches and then reverses direction. So what do we mean by that? It's like this, where it just nicks it just a tiny bit right there. Okay? So I'm going to get rid of that graph because we're going to make this a nicer graph. All right, let's go through and identify all the zeros. Remember, zeros come from each factor where you set it equal to 0. And yes, you can do this in your head. You don't need to show your work. X equals 2 is an x-intercept. So I'll put a nice clear dot there. All right, let's do the blue one. The blue one here is, this has a 0 of x equals -1. So I go to -1 and I put a big fat dot there. Easy enough. And then my fuchsia one here, x equals -1 is a 0 or an x-intercept, right? It's when the function would spit out 0. All right, so we'll go over here to 1 and we'll put a big fat dot. All right, so my function hits or cuts through those things. So who knows? Does it look like this? Or does it cut through and go up like that? Or maybe it comes down like this, or maybe it comes down and touches and then goes back up. Who knows, right? Well, we do. We can look at what's called end behavior to help us out. And we talked about the general shapes up here, the general shapes. So first of all, I know that it's not going to be upside down because this leading coefficient is positive. So I don't have to worry about the whole upside down thing. Actually, you know what? I'm getting ahead of myself. We need to talk about multiplicity first. So the odd ones are going to cut through. The odd ones are going to cut through. So the red one is going to cut through. So what I sometimes suggest to students is to like draw a little hash there. It's going to cut through. And then the fuchsia one, this guy is also odd, so it's going to cut through right there. However, at the blue one, that is the even multiplicity. So it's either going to do this or it's going to do this. Let's see here in a second what happens. All right, now let's talk about end behavior in the general shape. What degree is this? What degree is this polynomial? That's a little confusing, right? Because it's all factored out. What degree would it be if we multiplied it out? If we took, 3 minutes of our life, which I'm not going to do, and multiply it out, what would be the first term? It would be 3x to the 3x to the third, x squared, and x, all multiplied. To me, that sounds like x to the sixth. So we call that the leading term. The leading term is 3x to the sixth. All right, well, that's an even degree, isn't it? And then we set up here, even degrees do what? They do this. Even degrees, like parabolas, go up unless they're flipped over. They go up on both sides. So that's going to help us a lot, folks. I'm going to do this in, well, what color haven't I used? Let's use green. All right, so over here it's going to be going up, and over here it's going to be going up. You know what? There's only one way to draw this. There's only one way to sketch this. I'm not going to worry about the actual numbers. I'm not going to worry about the actual numbers. Here's the only way to draw it. It's got to just touch, come back, cut through, and then follow the end behavior on the right there. So let's go ahead and draw that in green officially. So it's going to come down like this. It's going to just touch. It's going to go up. It's going to cut through, turn around, cut through again, and then we have our shape there. So this is, after all, this was a x to the sixth graph. How many zeros did it have? Only 3. It could have had 6, but it only had 3 because of all the multiplicity mess in this problem. So those zeros are there multiple times. That's where the word multiplicity comes from, causing the number of zeros to not be 6, but something less. Isn't that cool? So multiplicity tells you whether it just touches it or it cuts through. And once you have end behavior sorted out, based on the shape that you know it needs to be, and whether it's opening up or down or what's going on, you can map out the general shape of it. Now, what did I mean by not using numbers? I didn't worry about the y-intercept or anything like that. I was just trying to get the rough shape of it, okay? All right, so you might want to pause the video and give this one a try. This looks like a good one. There's a couple special things going on in here, so pause the video, give her a try. All right, I do notice that this has a minus sign in the front, so it's going to flip things over. And again, we're going to talk about end behavior officially here in a second. I see x. So what would the 0 be for that factor? That's a factor. So what would the 0 be? It would be x equals 0. A lot of students forget about that one. So I'm going to come over here and put a nice big circle there. It's going to hit the x-axis there. All right, and then this one, x equals -1 is a 0. So I'm going to go to -1 and put a dot there. We'll do this one in black. This would be x equals 2. And then x equals 3. All right, so we have 4 different x-intercepts. Those are called zeros. X-intercepts are called zeros. All right, let's think about the degree of the entire polynomial now. The degree of f of x is, okay, so we have x to the first times x to the first, that's these two, times an x squared, that's this one right here, right? X squared, times another x to the first. That's a total of 1 plus 1 plus 2 plus 1 is 5. X to the fifth. It is a degree 5 polynomial. Now, normally a degree 5 is an odd one, right? It looks like this, possibly. But remember that minus sign? It flips it over. So the end behavior, let me go ahead and delete this. The end behavior, it's going to be something like this. So let's draw those arrows in. It's got to be going down over here and up over here. When you are a detective, what do? You lay out all your clues all at the same time so you can look at it and start to make sense of it. All right, I need to go back to multiplicity. I got excited and skipped that again. So multiplicity, we've got on the blue 0, that's an odd, so that's going to cut through. Let me zoom in here so you can see a little better. So on the blue one, we're going to cut through. What about on this one? This is also an odd multiplicity. Odd multiplicities means we cut through. So at the fuchsia one, we're going to cut through. Now at the black one, this is a multiplicity of 2. That's even, which means it's going to just touch. It's either going to be above or below. One of the two. And then finally the green one, this is another odd multiplicity, so we're going to cut through again. All right. We have all the clues we need here, folks. Here we go. I'm going to travel, well, let's travel left or right. We'll start up here. We're traveling down. We have to cut through. We turn around. We cut through. Now we turn around. We just touch. We go up, and then we cut through, and we connect to our end behavior. A really rough drawing, but you see that that one did just touch there at x equals 2. It worked out beautifully. So that's just a sketch. It's not an exact drawing. It's just a sketch of what it might be. All right, so let's get a little bit of the lingo done for end behavior, and then we'll be wrapped up with this video. This is what the graph will do when x gets really big. X going to infinity is really big, or really negative, really small. Okay? This is where you will need to know what the degree is of the polynomial. Now, depending on the degree, what we talked about happens in the shape. That has to do with the end behavior. So when the leading coefficient, let's add that in, and leading coefficient. So a sub n, x to the n. That's all we care about is that first term. So when the leading coefficient is positive and the exponent is even, our end behavior is like this. Now, if you're doing an assignment, often they use some different lingo, and I'm not going to use limit notation yet. We can save that for later in the year or in calculus. We're going to say as x goes to infinity, as x gets really big, the function outputs, that's what f of x means, are also going up. That's this guy here. Okay, so as x's get really big, the y's are getting really big, right? That's as we go to the right. I like to call that the right. So as we go to the right on the function. And then as x goes to the left, that's left, what's happening to the function as we travel the roller coaster backwards? So as we're going this way, we're going up again. So as we go to negative infinity, we're going to positive infinity on the outputs. So that's how you would write that one. Now, this is simply reversed. As we go to the right, the outputs are now going down to negative infinity. As x goes to negative infinity, that's called the left, f of x is heading toward negative infinity as well. So it's going down on both sides. All right, this is called end behavior, where you're just describing what the outputs are doing in the extreme, that's infinity, on both sides. All right, on the far left and the far right. So what about when n is odd? So let's do this one here. Actually, no, I'll draw the arrow up here. As x goes to the right, that's this way, this thing is going up to infinity eventually. So that's what we write. F of x is heading toward infinity. However, on the left, as we go to negative infinity, this is again when we have a positive leading coefficient, so as x goes to negative infinity, the function is dropping like crazy. It's going to negative infinity on the y-axis. So we're saying as x gets small, y's are getting small, very negative. All right, and then finally, well, I haven't used fuchsia yet on this one. As x goes to the right, that's this way, what are the outputs doing? They are dropping like crazy. So f of x is getting really big negative, very negative. Now as x goes the other way, negative infinity, the function is starting to output really big numbers. That's what we're trying to describe, what's happening in the extreme. All right, we have one more. Let's actually look at a little bit of algebra here. All right, so this is upside down, so we have a flip, and it's a fourth degree. Now, what do we know about fourth degrees? We know that they normally look like this. However, we're going to flip it over, and it will look like this. All right, so let's write that in our same notation that we did a moment ago. So as x goes to the right, the function is going into the basement. And then the same thing on the left. If we go to the left, the function is also going into the basement. The outputs are trending toward negative infinity. Not so bad, right? All right, and then finally one last one here. This is, all you have to do is look at this first one. That's an odd degree, and odd degrees are our John Travolta ones. Or I don't like to do this in the camera, like that. All right, John Travolta, you know, staying alive, staying alive. All right, it's going to look like this. It's going to look like this. So how do we write that? As x goes to the right, the function is going way up. That was this side right here. But as we go to the left, the function is going down into the basement here. Down into the basement. All right. Whew, that was quite a bit, wasn't it? All right, let's there it is. I was trying to get back to here. All right, well, hopefully you found this video useful, and now you know all about multiplicity and end behavior, and you're going to be our absolute rock star on your assignment. All right, good luck, and until next time.